Hello, 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 friend. Now this is the section for the machine learning, and that today the day one for the machine learning, and we will learn in this section about the Linear regression is the part of the machine learning, and what is the linear regression we will understand, and slowly we will understand, try to understand on the machine learning chapter. So the first is the I have prepared for a document for you. That's what is a simple way of the machine learning and what is the linear regression. So my name is Sima Bakhtar, you know well. I'm an instructor of your A to Z GIS class, and in this there's 30 days class, and this is a day 9 class. Okay, so now the first things before starting the linear regression, we we will try to understand what is the machine learning. So, the machine learning is a branch of artificial intelligence that enables computers to learn patterns from data and make prediction without being explicitly programmed. So, the term is a patterns is very important in machine learning. It follows a patterns. When we are talking about artificial intelligence or talking about the big data or others methods, so in the case of the machine learning, this is the very important for the patterns. So you are in a sitting in an interview and you are trying to speak about this definition of the machine learning. So you must tell about the patterns, because rainfall have a pattern, it's a flood effect have a pattern, and there is a, if a serial is coming on your TV screen, and that's the pattern. It's start from the episode 1 to the up to this course is also have a pattern from day 1 to this going to the day 30, and is a day 9. So that's the, if follow a certain patterns, that is the main signature of this machine learning. So we will understand what is the machine learning later. The first standard of we will try to understand the linear regression. So in types of the machine learning, the first is the supervised type of the machine learning. In this case, what is the supervised? So there are three types of the machine learning. The first is supervised learning. In supervised learning, both input and output data are available. Example: house price prediction, sales prediction, temperature forecasting, and others. These things. So in this, the main thing is that both input and output data are available. Okay, and main task was regression and classification. So second type of the this is the unsupervised learning. In unsupervised learning, only input data is available. Example: customer segmentation, clustering, and etc. So the third is a linear regression. So linear regression is the comprehensive notes covering definition and it's a part of the this linear regression unsupervised. In unsupervised learning, only input data is available. An example is customer segmentation, clustering, linear regression, and this linear regression the part of your this unsupervised. And the third one is mixed up supervised and unsupervised, that is called reinforcement learning. So we will learn about these things later. So come to the our part, this linear regression. So comprehensive notes covering definition, equation, slope, intercept, correlation, r square adjusted to r square, mec, gradient, descent assumption, advantage and disadvantage, and application we will cover in this section. So come to the introduction part. What is a linear regression? Linear regression, one of the simplest and most important supervised machine learning. Sorry, later I have told you the linear regression is a unsupervised, but it is a supervised. Okay. Sorry, the time is at 10:30, almost 11 p.m. in India. So a little bit I'm confused with this thing. So sorry for this. Now I've corrected my word. So linear regression is the one of the simplest and most important supervised machine learning algorithm. It means that it's have a input and output data. It predicts a continuous numerical value by finding the relationship between input variables and output variable. So what is the regression? Regression is a statistical and machine learning techniques used to predict continuous values such as sales, house pricing, groundwater levels, rainfall, and temperature. The simple equation you know from the your this school level: y is equal to mx plus c, and in machine learning form is a y naught y cap b naught and b beta 1 x. Beta naught is the intercept, beta 1 1 is a slope or coefficient, you know well. That's a simple school level equation, and this is a machine learning equation. So the intercept is the value of y when x is equal to 0. It's representing the baseline value of the target variable. So intercept is this. If you're talking about this, from if you're going to the integer, then it's means the origin. This means the intercept is 0. But in the case of the intercept present, then it's take the sum from here. This will go from here. This will go from here. This will go. That means something distance. So slope is a gradient. Okay. So the slope shows how much y changes when x increases by 1 unit. A positive slope means both variables increase together, and negative slope means one increase while the other decrease. Okay, that is the dy by dx things. Okay, this thing. So next thing is the prediction error. So prediction error is basically a actual value predicted this actual value predicted value is a good that is the actual value minus the predicted value, and it's a good model produce the small errors. It's in ideal case this must be a zero or these things. I think my screen is not visible to all of you, so I have to check it whether it is visible or not. Just get me the 2 minutes for this. This is the so yes, Sima Bakhtar. I uh, I come to. Okay, let me just 1 minute. Uh, I'm going to do these things. Okay, fine. Now I think this is visible to all of you. Okay, this is visible. Uh, Now it is visible. So fine. So next is this things. The error, how to prediction error. It's the actual value, that is your actual model, and this is a predicted value at this one. If this value is a very less, then we can say that this is a good model, and in ideal case this must be a zero. So next come to the it's a parts of the linear regression. Now next come to the this mean squared error. So MSE, that is mean square in 1 upon n sigma y minus y cap whole square. Errors are squared so that negative and positive rate do not cancel each other. So y I is the your in this actual value, and y cap I is the predicted value, and is the number of observation, that is and the summation. So this important thing is that why we are going to the squaring these things. So the first is squaring. Suppose the errors are there -2 and +2. If simplify, add them, then 0, it disappears. So therefore the we square the errors. So must be we will see in this case how much errors are come. So that's why we are getting the whole square taking this thing. So I think this is a fine to all of you. So next is the interpretation of MSE. Small MSE is a good model, and in ideal case this must be a 0, but no, there is no ideal case in this in this universe. So we have to try to as much as small as we place. So large MSE, a poor model. Gradient descent is a optimization algorithm that updates model parameters to minimize the cost function and reach the global minimum. So learning rate control the step size, very small values. Very small values, so learning very large values may prevent coverages. So these are things. So now for the correlation. So this is the very important thing, the correlation. Correlation is R measure the extent and direction of the relationship between x and y. Range -1 to +1. uh, Positive values indicate the positive relationship, negative values indicate the negative relationship. R square coefficient of determination, R square is equal to 1 minus SSRES and SSTOT. It means that how much variation in Y is explained by X. For example, R is equal to 0.285, mean that 85% of the variation is explained by the model. Okay, that's fine. So give me the 2 minutes break for this. I will just come. So welcome back to all of you. So now we will try to understand what is the correlation. So R measures the extent and direction of the relationship between x and y, range -1 to +1, and correlation and always dependent by the R. So positive values indicate the positive relationship, negative values indicate the negative relationship, and it ranges from the -1 to +1. So what is the R square? R square coefficient of determination, and its formula is R square 1 minus SSRES upon SSTOT. So it measures how much variation in Y accelerated by X. For example, R square is 0.85, mean that the 85% of the variation is explained by the model. So relationship between R and R square is that we will see here, the if R is 0.9 and R square 0.81, meaning that the 81% of the variation is explained. So next is the this one. So +1 perfect positive correlation, and this one plus 0.8 is strong positive correlation, plus 0.8 point 5 is a moderate positive correlation, 0 means no correlation, moderate negative correlation, and this is a respect with the R, and -1 perfect negative correlation. So r lies between -1 to +1. Remember that r is perfect positive, and this we have explained in these things. And now come to the equation of the this. We will try to understand the what is the your this one linear regression. Linear regression assumes that the relationship between x and y follows a straight line. The algorithm finds the base straight line that passes through the data points. This line is called the regression line for line or best fit line, and is represented by y is equal to mx plus c. And in the school level, you have must read this. So this is the line straight line of the equation, and in graph you can see this. This is your intercept, that is c part, and this is the slope. If you see the slope is this m, and dy by dx is your tan theta. You can depend by the tan theta or divide. Where I dependent variable output example sales, house price, and groundwater level. These are the example in real life. So x independent input example tv advertisement, house size, rainfall, slope of the line, c intercept. So but come to the we are reading the machine learning, and slightly change the this equation format in the uh, in terms of the machine learning. So here we will read the y cap is equal to beta naught plus beta 1 x, where y hat or y cap is predicted value, beta naught intercept, beta 1 is coefficient of slope, and x is the input variable. So understanding the intercept, beta naught intercept is the value of y when x becomes 0. Suppose the equation is cells is equal to plus 0.05, and this is the your cells of tv. And we will see in our python class, and this will be done in today. Okay, so this is the if tv advertising 0, cells is plus 0.05, cells is equal to 5, therefore intercept is equal to 5, meaning even without advertising the company is expected to sell 5 units. So understanding slope beta 1, slope tells us how much y changes when x increases by 1 unit. Okay, and this is tells us 5, so 0.5 in a tv. And here is a beta 1 is a 0.5. This is a slope, meaning the for every 1 unit increase the tv dependent, the cells increase by 0.5 units. Independent slope tells strength of the relationship, direction of the relationship. Okay, positive slope means when y-x increasing, y also increasing. Negative slope is y x is decreasing, then y is also decreasing. Okay, so if you have any doubt or problem, you can write a this chat section and chat box, any question and this thing. So next is your negative slopes when increase, and why we have seen. So age of machine and efficiency is the best example for this your negative slope with dominant. So how linear regression is work or learn. The algorithm tries many different lines. Some lines fit the data poorly, some lines fit the data well. The goal is to find the line that produces the smallest prediction error. The best line is called the optimal regression line. What is prediction error? Now come to the prediction as we have discussed in starting. The prediction error is the actual minus the your predicted value. So prediction error is the difference between the actual value and predicted value. Error is actual minus predicted. Example, actual cell 20 and predicted cell is 18. Then 2% is error is a small error means better prediction is there. And how much this is better and this is not better is a part of the statistics, and we will see the later. Okay. So cost function, a cost function measures how much error in the model, and this a cost function measures how much error exists in the model, and the objective of linear regression minimize the cost function. We will see in the this what we will see what we will see in this python class when we'll do the in this practical class. In the cost function, what is the cost function, we will try to understand. So the most common cost function is the mean square error, that is msc. We have read about the msc, and what the msc, we have seen the msc formula. That is the nothing but is the in the summation of this one of n and y minus y hat a whole square, and this is 1 of an n. We have seen in starting. So gradient descent, learning rate, and correlation, that's the part of the machine learning. So we have read about the linear regression. Okay, now come to, we are in machine learning, so some terms have changed. So we have to first understand what's the term. So the first is a gradient descent. Gradient descent is one of the most important optimization algorithm used in machine learning. The main objective of gradient descent is to find the best values to of the model parameters so that the prediction error becomes as small as possible. In simple linear regression, the parameters are the intercept, slope, coefficient, beta 1. The algorithm continuously update these parameters until the cost function reaches its minimum value. Basic idea: imagine that you are standing on the top of the mountain and your goal is to reach the lowest point of the valley. You can jump directly to the valley, so you take a small step downhill. After taking many small steps, you eventually reach the lowest point. The lowest point is called the global minimum. Okay, gradient descent works is exactly the same way. It starts with the random values from beta naught and beta 1 and keeps updating them until the prediction error becomes minimum. That's the fine. So updated equation: theta is new, theta old minus alpha del by del theta. So where theta is a model parameter, alpha is a learning rate, and z is a cost function. J is a cost function. Okay, that's the del j upon del d theta. Okay, that's the part of the fine. We are not going in a very deep way because it's a starting part of the machine learning, and we are trying to understand the machine linear regression, and this will be more clear when we are doing the this uh, Python practical. Okay, so the equation tells us that the parameter value should be the updated in the positive direction of the gradient because the gradient points toward the direction of the maximum increase. Now come to the adjusted R square, adjusted coefficient of determination. This is a very very important things. So R square coefficient of determination is one of the most commonly used performance metrics in linear regression. It measures the extent to which variation in the dependent variable y is explained by the independent variables x. However, R square has an one important limitation. Problem with R square: whenever a new prediction variable is added to a regression model, the value of R square either increase or remain the same. This happen even when the new variables has no meaningful relationship with the target variable. As a result, R squares can sometimes give a misleading impression that model is improving when it is in reality the additional variables are not contributing the useful one. To overcome this problem, adjusted R square is developed. Okay. Formula for the adjusted R square: 1 minus 1 minus in bracket 1 R and minus 1 upon n minus p1, where R square coefficient of determination and total number of observation, that is your data points, and p the total number of prediction variable independent of variable. So this is the, and remember that adjusted to R square are always less than your the actual R square. So why do we need R square? Adjusted R square solves the major weakness of R square. Unlike R square, adjusted R square introduces a penalty whenever unnecessary predictors and variables are added to the model. So if a newly added variable genuinely improves the model, adjusted R square increases. If a newly added variable does not contribute useful information, adjusted R square decreases or remains nearly unchanged. Therefore, adjusted R square provides a more realistic measure of model performance. So example, I will take a real life example. So the first is the this one. Suppose we have a house price prediction model. Model one variables house size and location, and R square is your 0.85. Okay, that's fine. Very good. Now suppose we add an unrelated variable such as a house color. Okay, then what happened? The R square value may increase slightly 0.85 to 0.86 simply because another variable was added. However, house color may have little or no effect on house price. Additional R square evaluates the whether the increase in performance is truly meaningful or not. Okay, that's the work of the R square, adjusted to R square. So if house color does not provide useful information, adjusted R square remain unchanged or even decrease. Therefore, adjusted R square generally preferred when comparing multiple linear regression model. So key difference between R square and adjusted R square. So R square always increases or remain constant when a new variables are added, does not penalize unnecessary predictors, can overestimate model performance. Okay, and adjusted R square, what's the work of this? Can increase or decrease, penalize unnecessary prediction, provide a more reliable evolution metric preferred or multiple linear regression. So assumption of linear regression. Now come to the assumption of linear regression, is a very important part. So before applying linear, several important assumptions should be checked. If these assumptions are violated, the model may produce unreliable prediction and misleading interpretation. Linearly assumption: the relationship between the independent variable x and dependent variable y should be linear. In simple terms, when x changes, y should change approximately along a straight line pattern. Example: TV advertisement increase, sale increase. If the relationship is highly curved or nonlinear, linear regression may not perform well. Secondly, independence assumption: all observations should be independent of one another. The value of one observation should not influence another observation. Example: if sales data from one day directly affect the next day sales measurement, independent may be violated. This assumption is particularly important in time series data. And normality assumption: the residuals errors should approximately follow a normal distribution residual. Residual is the actual value minus predicted value. So when residuals are normally distributed, statistical inference and confidence interval become more reliable. Normality can be checked using histogram, QQ plot, and Shapiro will test. Now come to the homoscedasticity assumption. Homoscedasticity means that the variance of residual remains constant across all values of the x. Okay, so in simple words, the spread of errors should remain approximately equal throughout the data set. Good situation residuals have a similar spread across all predicted values. Bad situation residuals becomes wider or narrow as x increase. So violation is called a heteroscedasticity. So it's a no multicollinearity assumption. This is a very important multicollinearity assumption. Okay, independent variables should not be highly correlated with each other. When predicted variables are strongly correlated, the model has difficulty distinguish the individual contribution of each variable. Examples: a variable house area, number of rooms. These variables are often strongly correlated. Highly multicollinearity may lead to unstable coefficient, incorrect interpretation, reduced model reality. Common methods for detecting multicollinearity: correlation matrix, variation inflation factor, BIF. Okay, so in summary, we have learned in the theory part. I know most of the things is overflow of your head, but this is the very introduction part, and my aim is to only understand your linear regression in terms of your machine learning. So this will be more clear when we are doing the practical part. Okay, now we are coming to the practical part. Let's just read this summary part. So we have read adjusted R square, an improved version of the R square that penalize the overfitting and provide a more realistic measure of model performance. Before applying linear regression, it is essential to verify the assumption of linearity, independence, normality, homoscedasticity, and no multicollinearity. Satisfying these assumptions helps ensure that the regression model produces reliable prediction and meaningful interpretation. Assumption: linearity, independence, normality of residual, homoscedasticity, and no multicollinearity. Advantages: simple, fast, interpretable, and useful as a baseline model. Simple to understand, easy to implement, fast training, easy interpretation, requires less computational power, and a good baseline model. Okay, Now come to disadvantage: sensitive to outliers, assumptions, linear relationship, and performs poorly for. Or these are the disadvantages of your linear regression model. Assumption and linear relationship: sensitive to outliers, cannot model complex non-linear patterns, affected by multicollinearity, and performs decrease when assumptions are violated. Applications: sales forecasting, house price prediction, groundwater labor prediction, climate industries, and agriculture and finance. So in business, sales forecasting, real estate, house pricing, and this we will see in our next one. So climate. So overall conclusion is that linear regression is the foundation of predictive analysis and machine learning, of supervised machine learning, and understanding slope, intercept, MSE, gradient descent we have seen R is and R square, and adjusted to the R square is essential before moving to advanced algorithm. So these are the part of the your theory part of your linear regression. Now come to the your this uh, okay, let me check right now. Open the Jupyter notebook. What will you do? The first things you have to install this Anaconda Python, and then you have to install the, which we have explained in the previous day two and day from day one to day eight class. How to operate the basics Python I have told you. Okay, Java servers password is token. No need to password. Okay, just give me. Mm, okay, now come to the before when you will start the your Python code. So you have to go and you have to sorry, you have to set your environment for running this code. The first things you have to go your this Anaconda prompt. Command prompt, Anaconda prompt. You have to open this one, and on this you have to set your environment for this machine learning. So I think this will be open. Just okay, this has been open when I Now when you will set the environment, this type of the windows will open. I have already set my environment, this Conda ML course, that is machine learning course. When I will click here, then this will open, and this is the open. And now I'm going to this things, download. In download section, linear regression is this yesterday. Okay, fine. We have come to the hour and this course, written by Seema Bakhtar, and this is the this is the code for your linear complete linear regression. We will do practical on a real type of data, and you will see the beauty of machine learning and linear regression. So you have first you have to set the environment for this, because most of the dependencies and packages are not work in your normal environment. So you have to adjust your this for environment. So the for this, I have already written for this setting update for the machine learning, setting up a separate machine learning environment for y data profiling. And what is the y data profiling? We'll see here. So why, the first question, why did we need a new environment? So the first, while working on the machine learning, we wanted to use from these things, why data profiling important profile report. So this is very important. What is this? We will see later. This library automatically generates a complete exploratory data analysis EDA report for a data set. This is very important. We have seen in the lots of in theory part. However, when you try to import in the default Anaconda environment, several errors appear, such as the attribute error, module Namba has no attribute generated JIT, and this thing. So, and module not found error, no module named PKG under resources. These errors occurred because the existing Python environment contain incompatible packages versions when you're using your normal. So you have to set this thing. So for overcome, I just choose them and set a environment and give the name is the ML course. That's why it is showing in my this Jupyter notebook. And you know well what is the Jupyter. If you are a paid participant of my course, then you know well. And I have already told you in a very simple way. So so to avoid modifying the main Anaconda installation and to create a clean machine learning setup, we created a separate environment called the ML course. This environment contains only the packages required for the machine learning course. So what is now second is the what is the Conda environment? A Conda environment is a isolated workspace containing its own Python version, libraries, packages, and dependencies you have installed or delete. Each one works independently. For example, base environment, GIS package, groundwater modeling packages, other software, machine learning environment, ML course, pandas, numpy, scikit-learn, matplotlib, y data profiling. These prevents packages conflicts. So I will take the 2 minutes break for this. Okay, come to the continue the this day one course. Hello. So creating the machine learning environment, the first you have to open the Anaconda prompt, and when you will install this Python and Anaconda and everything, then you will search in your Windows, then Anaconda prompt will appear, and this the Windows looks like this. Okay. Uh, Next is the run Anaconda create an course. This will be and explain these things. Conda create a new environment for this minus an closure environment name. You can change here. I'm just taking the ML course. This Python 3.1 and minus install Python 3.10 because my dependencies and this of course my Python 3.13, that is a very latest version, but some dependencies and packages will work on the old version. So that's why the need of this set up the environment. So directly this will work with the install Python 3.0, and why automatically answer yes. This will be yes. Yeah. So activate the environment, activate ML course. When after this will become okay base. When you'll change to this, when you'll come to the here, then this is the come. Okay, installing the your dependencies, pip install numpy pattern, these are the need for your install, or install the one times you can use this code. So fixing packaging resources error when importing y data profiling, be encountered the module not error found error, no module packaging resources. To fix it, pip install setup tools, and 8.90 verify Python C, import pkg resources, print okay, these are the things. So now when this is the okay, then go to your Jupyter environment. And how you know well how to go to the Jupyter Anaconda innovator, go to launch, and you will redirect your Jupyter environment. From here you will see the ML discourse, click on here, and this will open. Okay, now environment is open. So I just write here just this thing. This is my environment of the this one. See here the ML course, but this is your not in environment this. So this will not work in this, but this when I copy and paste in this, then this will work. Okay, fine. So next is that things. So start run, and these things we will see in our this uh, practical part. So let's start with practical part. So just copy and paste it. The first I want to tell about our data set. This is the advertising data set which I have downloaded from the internet sources. The first is the TV, radio. This is a self-priced newspaper, and these are the sales. These are things TV, radio 230, and these things, which I have collected data from the website. I will paste the in comment section from which type of the website I have collected. Okay, so now do it, and what is the correlation between these things? We will see here. Okay, just copy and paste these things and see the quick in our this. Okay, the current working directory is this one. We are coming in this where our data set has been kept. So run this very important these things. Why profiling, which we have read about this, because this is a very important, because it's a why profiling. We have read about these things. What is the why profiling? And we have seen this. What is a why data profiling? Why data profiling is a automated exploratory data analysis area library. It generates data set overview, missing values report, correlation analysis, variable distribution, status summary, and duplicate detection. And data quality with only one command. That's why we are doing this lots of the drama for set up our machine learning environment. Okay, from the Conda prompt. Okay, now run these things, why data profiling import and successfully, otherwise this will not work. Where I will run here, just see, this is not work, and it is showing the error, definitely showing the error, because this is not in my environment and dependencies are not working my normal these things. Okay, so and let's see, this is the starting and this is searching for my wife profiling data. So this is the error, but in this case when I'm running, this is a successfully run. So now come to import, since executable or not, we will check this one. Okay, checking now, fetching the our data set which I kept in my this path, advertising. Okay, now come to this df. Okay, data set we have in 200 rows and 4 columns are given. So I'm skipping some this tail and head commands which showing the first 10 entries and is showing the last 10 entries. So now I'm going to the df.describe, which gives you the statistical points. So see the lots of statistical value you have seen in this from this command for this data set, value cells and count, mean, standard deviation, and blah 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 things. Okay, now come to the main profile report df. What is this? And we will see. Now it is working. Now let's see its work and see what happened. See, now this has been open, lots of things in the variable, in four variable type 4 numerical variable and these things which we have seen. Okay, now column sets, tv columns and these things, you just see tv, and when you radio, just see radio, and you can see the statistic. Interest more details if you want to see industrial deviation curtices of this, you see this things conclusion table, you can see here table heat map, you can see maximum minimums count, you can see low and these things, and lots of things are from wider. Now come to the in a more detail, just run it. Now pf widgets. Okay, don't worry, some errors have come, so my work has done. So here, this is radio variables and tv, and you can see the lots of things here. Okay, cells and more details, numerical heat maps and blah blah things you can see. So here is the things df, pf df is this, you can export this. What is the error? Visit type not under the overview tabs. Okay, I will fix it, don't worry. Now this has been saved in this in html profile. So just see here, just see, you can see the lots of things in this numerical type and this, you can check for the cells, tvs, cell versus this radio versus this newspaper. So tables, lots of things are you can see and correlate with this, and so these are the way for the core overview variables, you can see intersection, see correlation. So wide data profiling, this is the beauty of the wide data profiling. Okay, you can do for your data set and things. So this is the end of the day one class linear regression, and from the machine learning points of view we have seen. If you have any doubts and things related to code and this theory part. So please message me on chat box or the others. So now I'm going to stop here. So we will meet in next class part 2, and we will see the in detail for the linear regression and do for the higher version of the regression part and machine learning part. So I'm going to stop here. So bye bye. We will meet in next class. Thank you. Thank you so much for watching this video.